Hello student to the course of physics of linear and nonlinear optical waveguides. So, today we have lecture number 35 and in this lecture we are going to calculate the effective area of the modes and we start a new topic which is related to optical fiber components. Okay, so in the last class if you remember we defined the effective area of a mode as this. By definition, this is over area, this is over area. So, by definition, this is the effective area. Now, we are going to calculate the effective area for a fundamental mode. So, for fundamental mode, we have psi 0 r as better to write is as psi r is psi 0 e to the power of minus r square omega square. Now, this is the field distribution, approximate field distribution that is given to you. So, this is for fundamental mode. Now, I am going to use this field distribution to find out the effective area which is defined already defined here. So, my A effective should be equal to 0 to infinity integration 0 to 2 pi, then mod of psi r whole square r dr d phi. This is the area element for in polar coordinate, because I need to use the polar coordinate here. Since the geometry is a cylindrical geometry, divided by integration 0 to infinity integration 0 to 2 pi, then psi of r whole to the power 4 and the area element. This field, the fundamental mode, this fundamental mode is doesn't depend on the phi. So, that is why this in this integration, this phi there is it will just going to integrate over 0 to 2 pi over this phi. So, there is no phi dependency inside this integration. So, that is why it should be simply 2 pi here, and in the denominator also it should be simply 2 pi. So, I can directly write it as 4 pi square, because it is a square associated with the numerator. So, it should be 4 pi divided by 2 pi, and the rest of the integration is integration 0 to infinity, then e to the power of minus of 2 r square divided by w square and then r dr, and it has to be squared, and we have here 0 to infinity e to the power of minus of 4 r square divided by w square r dr. Mind you, this is to the power 4, that is why this 4 will come here. So, if I now integrate this portion quickly, let us do that. E to the power of minus 2 r square divided by these things r dr. So, I can choose 2 r square as a new variable x, so that I can have 4 divided by omega square w square, then r dr equal to dx. Now, we will going to put this dr here. So, simply the equation will be w square divided by 4 integration 0 to infinity e to the power of minus x, because this portion I take x, and then dx. So, this is simply w square divided by 4, and if I execute this integration e to the power minus x, it will be e to the power of minus x minus 1 0 to infinity. It should be simply divided by 4. In the similar way, integration 0 to infinity e to the power of minus 4 r square r dr, one can execute that, and the result will be simply, I am not doing this integration because it is exactly the same procedure and one can find this value quite easily. So, eventually my A effective will be, we already have 4 pi square divided by 2 pi. So, it is essentially 2 pi, then it should be omega to the power w to the power 4 divided by 16, because I need to have the square of this quantity w square by 4, because it is square is sitting here, divided by this quantity. So, it should be multiplied by 8 of w square. So, it is essentially pi of a very straightforward expression phi of w square. So, you can see it is this omega, this w is essentially a spot size. So, if I know the spot size, then I can readily find out the effective area. So, if this is the field distribution, so let me draw in a different way. If the distribution is a Gaussian distribution, the field distribution is a Gaussian distribution like this, if it is approximated as a Gaussian distribution, then the spot size, if I know, then effective area I can calculate very quickly. So, this is the effective area of this corresponding field. We just draw this in the last class. So, this is basically the A effective, which is simply pi multiplied by the spot size square. Well, one can have one important empirical formula regarding the spot size and the fiber diameter. So, that I am just going to mention here, which is empirical relationship between spot size and A, where A is a fiber diameter. So, this relationship is something like this. This is purely empirical relationship and valid only for certain range of V. So, I will going to give you the range of V as well. So, V to the power 3 by 2 plus 2.879 divided by V to the power 6, and this is valid for the range of V 2.5. So, in this range of V, so what this empirical formula says, that if I have a V value in the range 0.8 to in between 0.8 to 2.5, that means essentially we are working in the region where the fiber is allowing only one mode or in single mode region, then for this single mode region only one mode will going to excite, and that is the fundamental mode. And we know that the distribution of the fundamental mode is Gaussian one. So, this is the distribution of the fundamental mode approximated as a Gaussian one. So, this is the fundamental mode, or rather write LP 01 mode. LP 01 mode, and for this LP 01 mode, depending on the value of V parameter, I can change the value of V parameter by changing the wavelength. Keeping A fixed, I can also change the value of V parameter by changing the wavelength or by changing the value of. So, let me write down what was initially the V parameter. It is A k 0 n 1 square minus n 2 square whole to the power half. So, it is A 2 pi divided by lambda 0, it is the operating wavelength, and n 1 square minus n 2 square whole to the power half. So, I can change the value of n 1 and n 2, and then I can change the value of V. I can change also the lambda 0 and I can change the value of V. So, if I change the value of V with this changing by n 1 n 2 or by changing lambda 0, then that value if I put here, I can have a ratio of W divided by A. If A is given, I can find out the value of the spot size. So, readily we can know that how the mode is distributed, what is the characteristics of the mode. The mode will be definitely a Gaussian type, but with these information, with this empirical formula, I can find out the value of the spot size, what should be the spot size of the mode. So, that is the useful formula. So, here W is a spot size. So, let me write it. So, W is basically the spot size, and A is the core radius of the fiber. Okay. So, with this I like to conclude the topic here, which is related to modes. Almost everything we covered here. Qualitatively we understand the mode distribution as well, and now we are going to jump a new topic, and that is related to the fiber optic components. Fiber optic based components. The fiber optics based components are very useful because we can have different kind of optical components. So, what are those components? Let me list it down, but before that, so this is used in many applications. So, these are the optical components. Optical fiber is not only used to just transmit light from one point to another point or information from one point to another point, it can also used as different optical components through which we can do many things. Used in many application, in especially in fiber optics based communication system. So, there are many components, fiber based component that is used in fiber optic based communication system. For example, like amplitude, or intensity components. What are these amplitude? Like coupler, very important. We will going to study this coupler in this course in detail. Then splitter, then amplifiers, etc. Also, we have a different kind of phase components. Like phase shifter, if I want to shift the phase, then phase modulator, if I want to modulate the phase. Then the polarization component, if I want to play with the polarization of the light. So, polarization components. Under polarization components, we have mainly the polarizers, which then I can have, say, wavelength based component, like wavelength filter, wavelength filters, or wavelength division multiplexing. Wavelength division multiplexing is a system where you can launch different wavelengths, and in the output these wavelengths can be separated out. Wavelength division multiplexers or demultiplexers. In short, it is called WDM. Also, we can have like some frequency components like frequency shifter, so the list is large. So, I am just giving you few of the names of the components that one can think of using the fibers. Now, we will going to choose one very important component out of that and try to understand the physics behind that, which is called the directional coupler. So, next try to understand the physics of the working principle of say directional coupler. So, definitely the name suggests that some coupling is associated with that, and this coupling is essentially the light coupling. So, I can couple the light from one waveguide to another waveguide, and as a result we can use this kind of system to different applications, and we will going to discuss this application in brief here. So, normally what happened here, we have 4 ports like this. Suppose I have a black box and I am having 4 ports, 1, say 2, say 3, 4. So, I am having 4 different ports here, and I can use these 4 ports for different applications. So, 4 ports. One kind of application is I launch a light here in 1, and I want this light to come in this fourth port. So, this is called the switching. I launch a light here with 2 different wavelengths, lambda 1 and lambda 2, and I want these 2 light to be separated in these 2 ports 2 to 4. So, I can have lambda 1 here, lambda 2 here. So, this is also called this is basically called the wavelength division multiplication that I just mentioned the last page, and so on. I launch a light here with a power P0, and I want this power to be splitted in these 2 branches 2 and 4, and it can be splitted according to my choice. One can split this light into 50-50, one can split this light to 30-40, whatever the ratio they want they can split. So, many application one can think of with these kind of systems, which in general called directional coupler. So, we are going to understand the basic physics and what is the mathematics or what is the physics associated with these kind of operations. Well, normally the most popular one is the fiber based couplers. In the fiber based couplers, what happened that, okay, let me draw quickly that I have a fiber like this, cut here, and inside that I have a core. So, this is basically my core of the fiber, and I have this, and then again from here So, I am drawing this is roughly the structure of a fiber base. So, now I have these two fibers, and these two fibers is, this is the core part, and this core part is placed very close to each other, and the cladding is defined here with the green one. So, the cladding can be removed from the fiber, and after removing the cladding I can put these two fiber very close to each other, so that the modes can talk to each other. So, this fiber and this fiber are placed very close to each other. So, what happened that if a mode is distributed here like this, and another mode which is distributed here, let us put in a different color, say this one. So, there is overlapping between two, and they will going to, there is a crosstalk between these two. So, they will going to talk to each other. If they are talking to each other, so there is a possibility that there will be some exchange of information from this to that in terms of energy, in terms of wavelength. So, that we are going to understand. So, this is the principle. So, this region is region where we have the overlapping of mode, and as a result, if I launch a light here, so what happened that something will happen in these two ports. Either I can distribute the light, I can distribute the wavelength associated with the light in two different ports, etc. So, I have 4 ports here also, like I showed here, and then I can distribute the lights in this way, so that I can have the exchange of energy here or exchange of information here. So, few applications, let me quickly point out that how many, what kind of applications one can think of. So, first is say switching. So, this is the port, this region, dotted region, and I have this one, and I am launching a light here. This is 1, this is 2, say no, this is 2, this is say 3 according to our notation, and this is 4, and the light will come here. So, I launch the light in port 1, and in the output the light is coming into port 4. So, this is called the switching. So, I can switch the light. Next application one can think of is the power coupler. In the power coupler, if I want to distribute the power from one port to another port, that also we can do. So, these are the 4 ports, 1, 2, 3, 4. I launch a light here, with the power say P0, and in the output I can distribute this power according to my choice. So, in both the ports I now have lights, and here I have light say P0 by 2, here I can have the light. So, I can distribute the power in a 50-50 distribution. This is called the 3 dB coupler, where I can distribute the light in a 50-50 portion, in 50-50 ratio. Next one can think of WDM, already I mentioned that, very interesting application one can think of. In WDM, what happened, this is the port, again I have 4 ports here. I launch 2 light here with 2 different frequencies. Okay, let me draw that in different color. So, I have lambda 1 and I have lambda 2. Two light are passing through this system. So, this is lambda 2 and this is lambda 1. So, I can make an arrangement with this coupler so that I can distribute the light here in this way. So, in this port I can extract the lambda 1 and in this port I can extract the lambda 2. So, this is, so you can see the structure is very important here, that it has to be very close, these 2 points has to be very close, so that we can have the exchange of energy. And when we have a exchange of energy, different kind of application one can think of, like a switching, like power coupler, like WDM, etc. In the next class, we will try to understand using a very important theory called coupled mode theory. So, we will try to understand using the coupled mode theory how these things is happening, the physics behind that. So, today we do not have that much of time to discuss the coupled mode theory. So, in the next class we will discuss the coupled mode theory to understand the physics behind these processes, how these things are happening in the real couplers. So, with that note, I would like to conclude my class here. Thank you for your attention. So, see you in the next class.